So it's a pleasure to have everyone here once for the second lecture of Professor Jaqueline Siqueira from the Federal University of Rio de Janeiro. So please, Jaqueline.
Thank you, Stefanella. So thank you all to have come back. Today, I guess we are doing a bit more light. Well, the proofs are going to be a bit more easier, and we are seeing some examples. So to make sure that you don't give up for next week. So that's the goal of today. So I'm glad that most of you are back.
Recording in progress.
I'm hearing some echo. Okay, thank you. I will pass again our panorama because, as I told you, it's impossible to deliver what you plan. So the plan changed. Probably you change again, but well, for today, the big plan is to see the Poincare recurrence theorem and a few examples. I hope at least 3, but maybe less than these. Let's see how we do with time. And let me put my time here. And the next week, then we enter in ergodicity and Birchhoff's theorem. Okay. So the main object that we want to study is invariant measures. So the biggest idea is to, well, we have a dynamical system. We want to understand the orbs of this dynamical system. By orbs, we mean, well, the iterations of the, if we are thinking of a map, the iterations of the map. If we are thinking of a flow, the trajectories of the flow. So how do we obtain information from the dynamical system via invariant measures? That's what we are going to see today. But just for recall, an invariant measure, or we can also say that it's the measure is invariant under the map, or the map preserves the measure. So I could also write F preserves. So time to time I'll change, say invariant or preserves. F preserves mu. If the measure of each measurable set is equal to the measure of the pre-image of this set. We already discussed that it's more suitable to choose pre-images than images. Then we also said that, well, what does it mean? This means that the probability of a point to be in a set it's equal to the probability of the image of this point to be at this set. Okay. For a flow, the definition is similar, but we need that each of the maps FT are invariant. For the each of the maps, it's invariant under the it's invariant for the measure me. So for all, now we change the discrete time to the continuous time. We change for T now in R. We just want, it's the same definition, but we want that this equality hold for all the FT. All right. We discussed the following problem. Is that in general invariant measures? So we have a way of creating invariant measures when we have periodic points. We just write a measure that is supported on the orbit of this periodic point, which is finite. So then it's quite easy to prove that this is invariant. It's a good example, but this is based on the idea that there are periodic points. But even when the map do not have a periodic point, does not have a periodic point, we can still construct maps. And the approach is similar to this. We start with a probability measure, and then we create a measure that is absolutely continuous with this probability measure that we started. That's what we did last time. So if we have a map that is continuous on a compact mapped space, we can always assure that there is at least an invariant measure. So invariant measures are very good objects to study because they exist in a very big context. We don't need to ask much. We didn't even ask some regularity on the map. We didn't need differentiability or anything. We only need at least continuity, and we need also that the space is compact. Obviously, there are cases when the map is not continuous or the space is not compact, and we still have invariant measures. We can not guarantee through this theorem, but there are cases where we can build invariant measures even without these conditions. Okay, so I mentioned briefly in the end of the talk a very good lemma that tells us the following. We don't need to check for all the measurable sets the quality that the measure of the set is equal to the measure of the pre-image of the set. We only need to check in an algebra that generates the big sigma algebra. This is very good, and we are going to use this today because, for instance, if we consider the Lebesgue measure, so remember, Lebesgue measure on R is only the length of intervals. Lebesgue measure on R2, it's only the area of sets. Okay, well, you have to formalize, there are more, but we are thinking a bit informally. Okay, for instance, if you want to, you have a map, and if you want to check if your map is invariant under this Lebesgue measure, which would be good, because remember, we have the delta, we have that measure that is supported in the periodic orbit. This is an invariant measure, but this is not a good invariant measure because it just sees the points that are in this orbit, just see a finite number of points. To show, for instance, that Lebesgue measure is invariant under some map, this is good because Lebesgue measure is a good measure. It measures things like, okay, the measure of an interval is the length of this interval. So you see most of the points. Fine. So let's say that that's your context. You have a map and you can define the Lebesgue map, the Lebesgue measure on the domain of this map. If you want to prove that this is invariant, you don't need to check for all the sets. In R, it's enough that to check for unions of intervals. Because this generates an algebra. Sorry, this is an algebra that generates the Borel sigma algebra. So we don't need to do it. In R2, you would do unions of arcs. But today we are not seeing R2, we are keeping our eyes in R. Another thing is that Lebesgue measure is the length of intervals. If you consider this in the whole space R, this is not a finite measure. The measure of the whole real line is infinite. So this is not a finite measure. But I could restrict this to an interval. If I restrict this to an interval, let's say the interval 0, 1, then Lebesgue measure there, well, the length of 0, 1 is 1. So it's actually a probability measure. So what we'll do in the examples is to restrict Lebesgue measure to the 0, 1 interval. Okay? This is gonna be more towards the end of the talk. But just for the, I'm not proving this lemma. This is not, it's not hard to prove. You can do as an exercise, but it's a good exercise. But there is a nice equivalence for the definition of invariant measures that we are not going to use today, but next week. But you can define invariant measure via integration. So once you define measures, it's natural the path to construct integration. We did this last time. And you can always rethink your problems of measures with, well, under some conditions, with integration. So we can say that a measure is invariant if and only if the integral of all the functions on R with values on R, it's equal to the integral composed with the map. To see this proposition in a more simple way, you can think of the following. Consider your map on R2. Your dynamical system F, it's a map on R2. And this preserves area. What does it mean? It means that the determinant of the derivative is 1 in modulus. So if this preserves area, the Jacobian is 1. And if you have a function that is Riemann integrable, then what we have here is actually the change of variables formula. It's exactly the change of variables formula. You would have to multiply by the Jacobian, but the Jacobian is 1. So this is a more general case of change of variables. So if mu is invariant, you can do the change of variables with f. F is a function that works for the change of variables. Okay? Fine. So let's finally enter in the world of Poincaré, which was the father of ergodic theory. So it's a very nice result, and the first way that we can see how we can extract information from the measure to the map. So I start with my, just a second, because okay, I start with a map that's measurable, only this. And then I consider an invariant measure, and here it's important that it's finite. In general, this theorem does not work for infinite measures, but it's finite. Invariant, let me make a comment that here the measure is just measurable. The map is just measurable. For the context where we have always invariant measures, it's continuity plus compact. We are not asking this for a Poincaré theorem, okay? It's only measurable. And let's say that, well, you got an invariant measure. For each set that has positive measure, almost every point, it's gonna return to this set infinitely many times. So you have your space, M, measurable space, and let's say you choose a set, can be small, but it has to be positive measure. That's your set here. And you know that maybe not every point, but almost every point with respect to mu is going to return to E infinitely many times. So, okay, you choose a regular point here inside of E, and then it can do many crazy things, but will return. And then can do a lot of other crazy things, but then it's gonna return again. So let's say this is Fn1, this is Fn2. Actually, it's gonna return infinitely many times. So it's continue return and return infinitely many times. So this already gives us some information about the auth. Well, I don't know what exactly happened to Fnx for all n, but I know that for infinitely many n's, you can think that there is a subsequence nk that Fnk belongs to E. Okay, what I mean by almost every point, I mean that except for a zero measure, there is a set inside, let's say, E tilde, inside of E, such that B E tilde has zero measure, and for each point in E minus E tilde, for all the points in the complement of E tilde, it returns infinitely many times, okay? The complement of the points that never return is zero. Sorry. the measure of the points that never return is 0. Okay, this is a bit less. That's not what I want to say. Let me explain again. Sorry, let me rephrase. I want to say that almost every point in E returns infinitely many times. It means that the complement of the sets of the points that return finite times has, oh meu Deus do céu. Sorry, once more and the last time, I promise. The measure of the set that the set of the points that return finitely many times is 0. That's it. That's okay. Okay. I apologize for this. So what we are going to do? So let's prove the theorem then. It's a nice proof. Then we have a map. Let me just recall here. That is measurable. We have a set that has positive measure, and our measure is invariant. That are our hypotheses. The measure is invariant. Okay. So what we need to prove? We need to prove that almost every point x, for me, almost every point x, there are infinitely many n's such that fnx belongs to E. Okay, so we start by doing the following. We define a set, we define E0 as the set of points that never returns. So E0, E0 is the set that never returns. My first claim is that the measure of E0 is 0. Okay, this is not yet what we want. I made a mess before, but that's not what we want yet. This is showing, okay, that the points that never return have this set has measure 0. We want that the set of points that return finitely many times has measure 0. So for a while, let's prove that this has measure 0. Okay, so first, if we take two naturals, distinct, bigger than 1, then the preimages of this set is 0. They do not intersect. Well, if they did, if there was a point there, let's say x belongs to this intersection. Okay. Then, well, I'll call y fn of x. So I took x, a point in this intersection, which I want to prove that it's empty. Then I want to arrive at a contradiction. Okay, so there is a point in this intersection. I'll call y the fn of this point. Fine. Then y belongs to E0 because x is f minus n is the nth preimage of E0. So fn of x, which is y, belongs to E0. Okay. Fnm minus n of y, it's exactly fm of x, right? Well, y is fnx. So when you iterate by m minus n, this is fm. Here it's m. I said that I would use the black version of these notes, but it didn't improve much my handwriting. So that's the best that I can do, people. Sorry. Fmx. Okay. This belongs to E0 also, because x is also in f minus m of E0. Okay. But E0 is contained on E. E0 are the points in E such that never returns. So E0 is contained on E, so this guy belongs to E. But it means that Y was in E0, so that was in E, and it returns to E after m minus n time. So then Y returns to E. But this cannot happen because E0 is the set that never returns. So no point in 0 can return to E. And this return, so it's a contradiction. Okay, so what we prove, which is important here, is that two preimages of E0, they are disjoint. Sorry. Fine. Okay, but since mu it's invariant, mu is invariant. By invariance, the measure of the preimage, any preimage of a set, is the measure of the set. So the measure of the preimages for each n of E0, it's E0. Well, the definition of invariance is that the measure of the first preimage, we are taking the nth preimage, but you just do it by induction. It's not hard. Okay, then we are able to prove the following. The measure of the union of the preimages of E0 for all n, this is actually equal to the sum of the measures of the preimages. Why? Well, this is because each of these sets, they are disjoint pairwise. So when we have a union, the measure of the union in general is smaller or equal of the sum. But when the sets are disjoint, then you can guarantee that it's equal. So this is equal of the sum. Okay, but the measure of each preimage, it's exactly the measure of E0. So we are sum, you have this sum of the measure of E0. But well, mu, it's finite. This is a set that belongs to the sigma algebra. So the measure of any set has to be a number, a finite number. Okay, so the left side is finite, so the right side should be finite also. But you are adding the same quantity infinitely many times. The only way that this is finite is if the measure is 0. So the sum of the numbers that you are adding, the number has to be 0. So this is 0. This implies that the measure of E0, it's actually 0. Okay? So you are adding infinitely many times the same quantity. The only way that this is a number is if this quantity is 0. And here, it's clear where we use the finiteness of the measure. This proof does not work if you take out the finiteness of the measure. Okay, we still didn't finish our proof, but now we are almost there. It's the easiest part. Now let's denote by F the points that return only finitely many times. Okay, so X on E such that Fnx belongs to E only for finitely many n's. Okay, so that's the set that we want that has measure 0, because then the complement is the set that return infinitely many times. If this has measure 0, then the complement is full measure. Okay, so how do we prove that this has measure 0? Note the following. For each point in F, well, it returns finitely many. So take the last time that it returns. you can always take the maximum. So it will return a few times, but you stop at some point to return. So take this number, let's say it's k. That's the last time for each x, there is a k that depends on x. But there is a k such that fk of x belongs to 0. Let's think. At some point it stopped to return. Let's say that the last time was k. But fk of x, it's not going to return anymore because you had x and then you apply fk, it's in e, but you never return. So if it's never returning, it's in E0 because E0 is the set that never returns. Fine. Then f can be, it's contained in the following union. The pre-image is by k of E0 for all k, right? Well, if a point is in F, then Fk is in E0. So the pre-image of E0 contain, for each point x, it belonging of the pre-image of by k of E0. So take all the unions, F is contained there. All right. Then the measure of F has to be smaller or equal than the measure of this union. Here I cannot say that is equal because these pre-images, I don't know if they are disjoint. They will not be in general. But I have an off with smaller or equal. Okay, and this measure, again, it is smaller this is smaller or equal because it's contained. Now that's what I want to say. It is smaller or equal to the sum of the measure of all pre-images. Zero to infinity. Okay. But, well, so I'll copy again. I had the sum of the measures of the pre-images of E0, 0 to infinity. But now again, the measure is invariant. By invariance, the measure of all these pre-images is the measure of E0. So this is the sum of the measure of E0. But E0 has measure 0, you already proved it. So you are adding 0 infinitely many times. This is 0. So this proves that the measure of F is 0. So the complement of F is the set that returns infinitely many times, so has full measure. Okay, so almost every point returns infinitely many times. Just for make a note, we can extend easily this for flows. For flows, this result also works. And it's enough to note the following. You have the flow, Ft, and then you can, it means that if mu is invariant for the flow, it means that all the Ft's are invariant. So mu is invariant for all the Ft's, for all t. In particular, it's invariant for F1, the time one map. So knowing that is invariant for the time one map, you can apply this recurrence theorem that we already proved and show that the points return infinitely many times. But if return infinitely many times for this one, return for the flows. So it's easy. Just apply for the time one map. Okay. Okay, that's the first application, the first result that we can see how we can obtain some information through the measure. So if you have a invariant measure, you know that your points, you don't know what exactly is Fn, but you know a bit of the asymptotic behavior of Fnx. For almost x, Fnx returns infinitely many times. Okay. We can change a bit the context and change a bit the setting and go for topological spaces. So this is the topological version of the theorem. You can state the following. Well, first let's define what's returning mean in the topological set in a more precise way. So we have a topological space, and we consider the Borel sigma algebra. Recall, the Borel sigma algebra is the sigma algebra of open sets. Again, have in your mind the example of Lebesgue measure with open intervals generating it. Okay. So we say that a point is recurrent for the map if there exists a sequence such that Fnj converts to X. What we are saying? Well, you have your space M, and then if a point is recurrent, you don't know what exactly happened to the Fn, but you know that there is a sequence that's converging to it. So the point can do some crazy stuff, but it will have to be passing here, close to the point X. Let's say X is this black point, and the rest is the orbit of X. Then you start to apply F. Okay, it can do a bit, can stay a finite time here, but then goes and stay infinitely many times very close to the black point, and then can go around the space, but it has to return infinitely many times here. It can happen that a recurrent point has a very strange orbit, but you know what is going to happen in the future. You are knowing that it's converging to the point, it's coming back to the point. Okay, so the recurrent points are very important. This is the points that are not recurrent, they are not converging anywhere. So let me rephrase it. In general, what I'm going to explain better this concept next week, but just for give an idea, in general, that are the points that we are willing to check what happened with the recurrent points. Okay, these are the good ones that we have interest in dynamics. Okay, that has a nice dynamics. The other ones are the non-recurrents are not so interesting because we know what is going to happen to them. Okay, so the topological version for the Poincare recurrence theorem says the following. You have this topological condition, this extra hypothesis. You need that your space, the topological space, have a countable base of open sets. Many spaces have it. It's not a huge request. It's not to request much. Okay, very good space have. But if you are, for instance, study functional analysis, you know that not all of them have this base. So let's put as a hypothesis, this is important. We need this. So again, you have a map measurable, the same condition for the other version. The measure is finite invariant. The only difference is this topological condition. And the result says that, well, almost every point is recurrent. So almost every point is recurrent. It's saying the following, that except for a measure 0 set, everyone is recurrent. So the whole, what's really important for the system is the recurrent point. So you can throw away the others. The others has a measure 0. So you already know that where to study. This is giving you an idea to which kind of points you should study. You should study just the recurrence because the rest has measure 0 with some invariant measure. Okay, so let me give you the proof of it. It's even easier than the other one. And these are very nice proofs I like. I hope you also enjoy a bit. Okay, so the theorem, let me repeat so you don't forget. You have M, you have a countable basis, let's say UK, okay, of open sets. Each UK is open. You have a map, the same hypothesis now, measurable, and a mu which is invariant. Okay, so what you want to prove is that almost every point it's recurrent. It's recurrent. Okay, so notice the following. Before we had that in the other version, we had that a set with positive measure, almost every point return infinitely many times to this set. So it's more local. Now you have a condition that you define for the whole space. What's recurrent is to have a sequence that converges for this sequence, the iterates converge to the point X. Okay. So what we are saying is that almost every point in the whole space, so we are not localizing on a small set. We are saying that for the whole space, almost every point is recurrent. Okay. So let's have an idea how to prove it. So for each K, I will consider the UK tilde, all the points on UK, such that they never return. Okay, never return to UK. This we already saw by the last version of Poincaré theorem that this has measure 0. The measure of this set is 0, because that is our E0, no? But for the UK. So for each UK, consider the points that never return. This has measure 0. Okay. So the measure by the last version, by Poincaré, the measure of UK tilde is 0. So then, if I consider the union of all the UKs, tilde, the measure of U tilde is also 0. Because each of these is measure 0. When you sum of all of them, you'll be measure 0. So this measure also is 0. Fine. So the claim, the only one for this proof, is the following. X does not belong to U tilde. If it's in the complement of this set, then it's recurrent. That's enough to prove the theorem, no? We want to prove that almost every point is recurrent. We are proving that the complement of if a point is not in a 0 measure set, then it's recurrent. Yes, I can. Guilherme is asking to repeat the definition of UK. UK is the base of the topology. For hypothesis, there is a countable base of open sets. So UK is the base of the topology. So our open sets a base of neighborhoods. Okay, UK tilde is the points in UK that never returns to UK. Okay. Okay, you're welcome. Fine. Then the measure of all these UK tilde is 0. So I took the union of all these sets of 0 measure. So the measure of the union has to be 0 also. And now we are claiming that if X is not in U tilde, then it's recurrent. And that's enough to prove the theorem. So let's prove the claim. Okay, take a point that is not in U tilde. Well, it's in M, but not in U tilde. And consider U some neighborhood, some open set, a neighborhood of, I'll not write neighborhood because I always confuse where there is H. U, it's a neighborhood of X. Okay, so by definition, well, UK is the base of the topology. So every time I have a neighborhood, it should exist an element in this base such that it's contained in U and contain the point that I'm fixing. So U is the neighborhood of X. So by definition, there exists a K such that UK is contained in U and X it's in UK. So there is an element of the base of the topology that contains X and it's inside of U. That's the smaller neighborhood. Let's think like this. Oh, sorry. Okay. So since the point X that I consider it's not in U tilde, then X is not in UK tilde, because U tilde is the union of all the UKs. So it's not in any of them. In particular, it's not in the one that I fixed the K. Okay, then it means that there exists some N such that Fnx returns to UK, because UK tilde is the set that never returns to UK. So to say that X does not belong to UK tilde means that it returned to UK at some point. So at least once. Okay, the opposite that never returns, it returns at least once. So it has to return at least once. Fine. But UK, it's contained in U. It means that Fnx belongs to U. So it means that, what did I prove? Well, I start with a point that does not belong to U tilde, and then I gave an arbitrary neighborhood of it, let's say U that depend on X, it contains X, an arbitrary neighborhood. And I prove that there exists an N such that Fnx belongs to U. If you use a smaller result from topology, you know that this means that there is a subsequence of Nx that converges to X, because the neighborhood that I chose was arbitrary. Okay, so what does it mean that a sequence converges? It means that for each neighborhood, you can find after some point you can find infinitely many points inside of this neighborhood. But we want to prove not that the sequence converges. We want to prove that there is a subsequence. So for each neighborhood, there is at least one point inside of the sequence inside of this neighborhood, and the neighborhood is arbitrary. So this ends the proof of the topological version. So this proves that, okay, if we have a measure that is finite, it's invariant, then almost every point is recurrent. It means that Fnj converges of X for almost every point converges to X. So basically, what is this theorem is giving, well, many other applications that we'll see in the examples quite soon, but at least it's giving you a very nice way of looking to your dynamics. You wanted to study all the Fnx. It's quite hard. This is a difficult problem for each X to study as well. Throw away part of your system. There is a part of the system that has measure 0 that's not relevant. So the rest, you know what's left. It's left only the recurrent points. So you can restrict your idea to study the recurrent points. This already gives you a lot of information. It appears that it's not, but it gives you a lot of information. At least it restricts your word when you want to study. But let me just comment, as I said, sorry.
There is a question in the chat.
Because if it was not countable, I would not know that this is measure 0. This has measure 0. Who asked me? It's Assad. Okay. When I make the union, and I know that the union belongs. Sorry, I would not be able to count this to measure it, because what we did. Assad is asking if someone didn't.
Yes, I understand. Thank you. I understand.
You understood?
I got the point. Thank you. Yes.
You got the point. But I'll comment because it's a good point that I didn't make it clear, I think. I asked that the base is countable, and what I did here, I did the union of everything. Fine. I can do it always. It didn't need to be countable. I could take the union, but I would not be able to measure it because I don't know if the union of measurable sets, each union it's measurable. A countable union of measurable sets is measurable, but any union I don't know, so I would not be able to measure it, and I would not have this point. That's where we use it. Thank you, Asad, for the question. All right. So let me make the comment that, well, we just commented. Yes? Okay. So we just comment that countable countable base of neighborhood is important, but finiteness is also important. So a very simple example that we could do is to take the map on R. I already commented that Lebesgue measure is not finite, it's infinite. So let's consider this map, just do a translation, just do x plus 1. Okay? So we know that Lebesgue is infinite. Né? Okay, but it's also invariant. I let it as an exercise. It's not hard to see that this is invariant. So just think what is the pre-image of any set. Fine. But no point is recurrent. Let's think a bit. What is the dynamics of this map? You take a point and you translate. You push a bit in the line. No point's gonna return. If you continue apply, you push one more. If you apply n times, you add n. So you just push to the right or to the left. So a bit, no, always to the right, even if it's negative, of course. So you just push to the right a bit. So it's not gonna have any recurrent points. So the finiteness is really necessary. So we can have the same setting, and here we have a countable basis. We are in R. But still, we don't have the result because we don't have finiteness, and that's the point. So finiteness is necessary. Okay, so just for finishing and give some examples. Let me check my time. Okay, we can combine. This is called the Birkhoff's recurrence theorem, and there is a nice proof of it, without giving the ideas that I'm giving here. But since we already did the existence of invariant measures, we can derive this theorem easier. But I didn't put the name here of Birkhoff because the Birkhoff's theorem in Ergodic theory you will see next week. So Birkhoff did many things, but let's keep the name of Birkhoff theorem for the ones that we are seeing next week, which is the real Ergodic theorem. But this one is important because you combine these two, recurrence and the existence of invariant measures. This says the following. If you are in the setting of the existence of invariant measure, which is, I have a map that's continuous on a compact map space, then there exists at least one point that's recurrent. Because, well, if you have continuity and on a compact map space, you always have invariant measures. I'm doing the proof here. So there exists me invariant. This by the existence, the theorem of existence of invariant measure. Well, by the Poincaré theorem, almost every point it's recurrent, but almost every point may not be much. Think that if your measure was the Dirac on P a fixed point. This measure, if P is a fixed point, this measure is always invariant and just see one point. So almost every point for the Dirac, it's 1 point. So the most that we can guarantee that at least 1 point is recurrent. But at least we prove that the set of recurrent points are always non-empty. So that's what's the idea. We don't need the existence of invariant measure to prove this theorem. We can do a direct proof, that is Birkhoff's proof, using the Zorn's lemma. But what I use to prove existence of the invariant measure is the weak star topology. I use that the set of all the probability invariant measures is compact with the weak star topology. And for this, we use the Hahn-Banach theorem. And for proving the Hahn-Banach theorem, we use the Zorn's lemma. So basically, the proof is the same. It has different paths. So I suggest, if you want to check this proof with using the Zorn lemma, if you are aware of these results from function analysis, it's a nice thing to check. But faced with we already have, we can do a very easy proof. Okay. So let's end up with some nice examples. So these are the classical examples that one should see. It's necessary to continue life to see these examples at least once in life. So let's see them. Let's do our duty. Okay. So the doubling map, it's a map that doubles things. Okay, so I consider the doubling map a map on the 0, 1 interval on R. All my examples for today are going to be on R to start simple. Next week, we'll see other examples in other spaces. So I consider the Lebesgue measure and the Borel sigma algebra. Let's remember that I said we can think of the algebra generated by unions of intervals. These generate the Borel sigma algebra, that is the smallest sigma algebra that contains all the open sets. But for checking anything for invariant measures, you can restrict to unions of intervals. Okay, so the doubling map is the map that is 2x modulus 1. Well, we can rewrite this by saying that it's 2x if x is smaller than half, and it's 2x minus 1 if x is bigger than half. So it's basically, the graph is these two branches, and two branches that I'm very proud that I managed to do this picture by myself. I always steal from someone doing the credit, of course, but this time I did the pictures. This is a good consequence of pandemics. I learned how to use some things. But anyway, so this is very simple graph, but gives you some information. So it's doubling. Now you have here is the half. And then you have here the same image that you have here. So let's think about this. So what we want to prove is that Lebesgue measure is actually invariant under this map. What do we need to prove? Well, we need to prove that the measure of each set measurable, it's equal to the measure of each preimage for all the sets. Well, not for all the sets. We already mentioned that we can just look for unions of intervals. Let's choose just one interval and see what happens. Take one interval, and what's the preimage of it? Let's say this is A. Well, the preimage of it is going to be one interval here and another interval here. So it's the union, the preimage of an interval is the union of two intervals. My drawing is horrible, but if you do the computations, you will see that the length of the interval A, let's say this is A1 and this is A2. It's A1 is half of the length of A, and A2 has half of the length of A. So the preimage of any interval would be, by the first part, the first branch, divide by 2, and by the second branch, you have to add 1. So this is, well, This means that the length of this pre-image, it's this sum, which is exactly the length of the set. So if you start with an interval, it's easy to make the computation, is done here, to show that the Lebesgue of the pre-image is exactly the Lebesgue of this interval. Well, you need to consider disjoint unions to generate the algebra. But then it's easy. If you have disjoint unions, it's not so hard to prove that the Lebesgue of this, well, this is immediately the Lebesgue of this union is the sum of each of the length of the intervals. And it's not hard to check that the Lebesgue of the pre-image is equal to the Lebesgue of the image of the set. Because we use this, you know, this expression of the map, and then you can do the computation like I did here for a unique interval. So this proves that Lebesgue is invariant under this map. Well, we can generalize a bit this map by considering it's something related to this doubling map, is the decimal expansion. So I will consider the map that is 10x minus the, how I call it? I forgot how to call it. It's the floor 10x. I mean, what I want to denote is the 10x minus this number is the fractional part of 10x. That's what I want to say, but I forgot how to say this function in English.
Is a bracket function, I think. 10x mod 1 in some sense, we can say.
It's 10x mod 1. It's 10x mod 1. I write like this because it's easy. So what I want to say is that this means that this is the greater integer less than or equal to 10x. Okay? So this is the floor map. I think it's called like this in English, the floor map. Okay, thank you. So for each x, the fx is the fractional part of 10x. So we can do a graph, not hard. And now instead of having 2 branches, because we have the doubling map, now we have the decimal expansion, so we have 10 branches. But they are all equal, all linear, and easy to understand. What happened here now if I consider Lebesgue? Well, I want to prove that the Lebesgue is invariant. So if I get an interval, which would be the pre-image of this interval? Well, it would be nice if you could see better, but it's not hard to see that we have 10 small intervals disjoint. In each branch, you have an interval for the pre-image that has the length 1/10 of the initial interval. So it's not hard to prove that the pre-image, it's just the union of these intervals. Each has the same length, 1/10 of the initial interval. So the length of the pre-image is exactly the length of the interval. So you prove this for an interval, and then you can extend for unions. It's not hard. I'm not doing this computation because it's gonna appear more harder than the doubling. That's why I did the doubling map, to convince you that this is easy. But graphically, you can believe that this is easy to prove. So then Lebesgue, it's preserved. And now let's use this to show something completely different. So the question is, I want that to show that almost every number whose decimal expansion starts by 7 has infinitely many digits equals to 7. Okay, so consider the number between 0 and 1. Look at the decimal expansion. I want that you prove that each point, almost each point that starts with 7, 0,7 something has infinitely many digits also equals to 7. So let's use invariant measures. We have already one. Lebesgue is invariant. Okay, and let's think about Poincaré theorem. Almost every point returns. Okay, so saying this, let's rewrite the problem. Okay, so we have a point between 0 and 1, a number. We can also write in the decimal expansion, but let's suppose that this number is written, okay, the digits are between 0 and 9, but we do not have infinitely many 9s, just to not have a problem with the 1. Okay, so you wrote the decimal expansion, fine. And the only request is that your expansion do not have infinitely many 9s. Your map is the decimal expansion. What does it do? It takes it's the fractional part of 10x. So when you apply f to x, you multiply by 10, you put the comma here, but then you take the fractional part, then it's 0, comma, a1, a2, a3. You throw away the a0. Basically, that's what you do. So to apply the map to a number written like this, it's very easy. You just throw away the first digit. Well, how it will be f2? If you apply f again, well, you multiply by 10, the comma is going to be here, but you take the fractional part, then you throw away the a1. So f2 of x, it's going to be 0, comma, a2, a3, and so on. So then it's easy to compute fn, which is always our dream. Okay, fn is just 0, comma, an plus 1, and so on. So to apply fn, you throw away the n first digits. So your decimal expansion starts on an. Notice that we start on a0. A0 is the first digit. Okay. Sorry. Okay. So now let's consider the set of all the numbers whose decimal expansion starts by 7. So this set is only the sets written like this: x with the decimal expansion, a0 is equal to 7. Well, Lebesgue measure is invariant under F. So by the Poincaré recurrence theorem, almost every point in A return infinitely many times to A. Well, we have to check that we have to note that this has measure positive. It has, no? It's positive measure. It's a small interval on the line. So this is an exercise to check that the measure of A is positive. Lebesgue measure of A is positive. It is. So since it's positive and Lebesgue is invariant, we already proved that it's invariant, then almost every A returns to infinitely many times to A. What does it mean? It means that for almost every number in A, there are infinitely many values of n such that fnx is in A. But fnx was exactly, well, 0, comma, an plus 1, and so on. So it means that if fnx belongs to A, it means that the first digit, which now it's an, it's 7. So an is 7, but we showed that infinitely many values of n, fn belongs to A. Well, infinitely many times an is going to be 7. So this is exactly saying that in the decimal expansion of x, infinitely many times we have a 7. So we just look at our problem, which was a number theory problem, with the ergodic point of view. We introduce a map and we solve it using the recurrence of Poincaré. Okay. Well, calma, before the spoiler. So almost every number in A has infinitely many 7s in its decimal expansion. So the first question is, well, this was the 7. If I choose, my favorite number is 7, fine. But maybe your favorite number is 3. If you choose 3, what could you prove? Well, you could prove the same thing. 7 has nothing special for my sadness. There's nothing special here. We just choose fix one digit. And then you say, okay, the first digit is 7. But you could have said here, take A, the set that the first digit is 3 and complete the proof. So what I can say is the following: for each digit, almost every point in the decimal expansion will have infinitely many repetitions of this digit that you fix initially. Well, moreover, we will prove, that's a spoiler, that almost every point it has infinitely many digits, but we can say that the frequency is precisely 1/10. What we expect, there is no preference of points, of digits. Between 0 and 9, each of them appears with the same frequency 1/10. For this, we need the ergodicity, and this is what we'll see next time. I think I pass a bit my time, so thank you for the patience. I can never get to the end, so I can never get to put my thank you slide because I prepared too much, but that's it. Thank you for today.
Thank you. Let's thank Jaqueline. Very good, very good. So question, open to question. Let's see, more questions.
Well, people are a bit ashamed, but please, if you want to ask question.
I believe I have a question, but I don't even know whether I know how to properly formulate it or not. Because I mean, it's regarding the beginning of the lecture. Actually, we talked about a bit, just reviewing, right, the last class, and talked about
Yes.
these invariant measures and all that, and how the Lebesgue measure would be an example of an infinite measure on R, right?
Yes, yes.
For example, if I wanted to work with probability measures instead and consider, I don't know, dynamics regarding some functions that keep these probability measures invariant, for example, I don't know, the exponential of minus x squared or something, that is definable over the whole real line and which integrates to a finite value. I mean, would it be?
I didn't understand so much the question. Okay. Let me maybe try to understand. Okay. The point is that in general, when you define Lebesgue on the whole line, yeah, it's infinite because the whole line, the measure is infinite.
Yeah.
You can still do dynamics. You can still do ergodic theory. There is a whole line of infinite ergodic theory. I'm not a specialist on it, so I don't know much. I know a bit what I studied during my PhD, but I've been not studying it. But there is a whole field on it, so you can do a lot of things. Okay, but let's say just of our tools, what you can do. Yeah, you could do, for instance, if you are studying a map that does not take much values on outside of compact sets, for instance, then you can still consider Lebesgue in the whole space. But what we do in general is to restrict to some, instead of think about a specific map, we restrict the domain, like we did today. This is the easiest path, but yes, there is also this approach of thinking the map does not take values, or it's not gonna be, the image is not gonna be outside of some compact, then it's enough to consider Lebesgue. Stefania, maybe if you stop the recording,
yes.
we'll be less ashamed to talk. But good question.